Teen Physics. Okay, so today's screencast is about slopes, and this is important because using the slope of the position versus time graph, you can actually calculate the velocity versus time graph. And this is actually something that I've been seeing you all do in class by yourselves. You kind of intuited this, it made sense to you, and you're doing it already. And this screencast is just a way for me to formally break it down for you. But I think you'll find that watching the screencast, you'll see that you've already inferred most of it already, just given what we've been doing in class. Okay, so the slope. The slope of a line can be calculated. It's equal to the rise of the line, so how much it goes up. So this is the change, delta means the change in y, over the run, or the change in x. So we're going to be calculating slopes of position versus time graphs and using them to create velocity versus time graphs. So we'll start with something really easy. Going down here, I've just screenshotted a bunch of different position and velocity versus time graphs from MatchGraph, and we'll start with the first one right here. Actually, I'm going to make these all a little bigger. One second. Okay, so for each of these, I've got a position versus time, and right next to it, a blank velocity versus time. We're going to be talking about how to calculate the position versus time, or using the position versus time, how to calculate the velocity versus time graph. So, like I said before, that the slope of the position versus time graph is actually going to tell you what the velocity versus time graph is at every moment in time. So let's just start with something that's really easy. So for this graph, notice here that we're standing still, and we know that because the position doesn't move up or down, the y-axis. There's no change in y, even though we're progressing through time, so there is a change in x. So we're standing still at 0.2 meters per second, and then the time is going from 0 to 10. So very quickly we can calculate the rise, so the change in y over the change in x. Well, y doesn't change at all, so the change in y is equal to 0. Divided by the change in x is 10 seconds. So this is 0 meters again. So overall, our slope of this line is 0 meters per second. So that's our entire velocity, this whole thing. So we can just draw that right in here. 0 meters per second is our velocity. So again, the slope of this line is giving us the velocity. Okay, moving on to something a little bit more complicated. Now, we have a delta y and a delta x. So in this graph, we start at 0.4 meters away from the motion detector, and then we move up to 1.8. So our delta y, our changes in y, is equal to from where we end, so 0.8 meters minus 0.4 meters. So our delta y is equal to 1.4 meters. Okay, that's our delta y, and then our delta x, again, we end at 10 seconds, and then we start at 0 seconds, so our delta x is going to be equal to 10 seconds. So to calculate our slope, we could say 1.4 meters divided by 10 seconds is equal to 0.14 meters per second. And so we have a constant velocity. In this line, you know, this whole time we're moving at 0.14 meters per second. You can kind of check your work here. You can just look, okay, over the course of 1 second, I should move about 0.14 meters. So if I start at 0.4, I should end at 1 second at about, 0.54, which is, that looks like 0.5 would be right about here, and 0.54 would just be a little bit higher than that. So just spot check your work. Seems like we're in the right ballpark here. Okay, so that is our constant velocity for this line. And again, we're moving away from the detector here, And you can see that it's a positive slope of this line. So our velocity versus time graph is going to look like this, a straight line at 0.14 meters per second. Voila. Okay, a little bit more complicated. Now we have a line sloping down. We start at 0.8 and we end at 0.4. So we have to take our final position, so 0.4 minus 1.8, and again, this is meters. I shouldn't forget to use my units. So that's going to give us a negative displacement, or a change in position. So we end up with negative 1.4 meters. We've gone back towards the motion detector. But again, we've ended at 10 seconds minus 0 seconds where we started. Oops, that looks like a 10, but it should be a 0. So we end up saying negative 1.4 meters divided by 10 seconds is going to be equal to negative 0.14 meters per second. So when we look at the velocity versus time graph here, or when we create it, we're going to have negative 0.14 meters per second. And maybe I should label these. So this is going to be 0.14 meters per second. And this one is going to be negative 0.14 meters per second. And again, spot check your work. Over 1 second, we should be losing about 1.4 meters, and you can see here that that is going to be true. We've changed about 1.4 meters from where we started over the first second. Okay, even more complicated. So first we have to calculate the delta y and the delta x for this little segment of the line. So the delta y here is 0, because we start at 0.4 and we end at 0.4. So 0 meters displacement divided by 1 second is going to be equal to 0 meters per second. So between 0 and 1, we are going 0 meters per second. So we can plot that in on our line right here, going 0 meters per second right there. And then next we have to look at this section of the line right in here. I'm actually going to undo that. This section of the line right here. So we go from 0.4 to 1.4, so 1.4 meters minus 0.4 meters is equal to 1 meter, over how many seconds? Well, we go from 1 to 2, which is 1, and 2 to 3, which is 2 seconds total. So, and you can also say you end at 3 seconds, and you start at 1 second, so 2 seconds. So 1 meter divided by 2 seconds is 0.5 meters per second. So between 1 and 3 seconds, I'm traveling at 0.5 meters per second. And again, it's a positive slope. Rise over run is positive. So this is going to be positive. So then I can jump up here. And for 2 seconds, I'm going at 0.5. Then, notice here, I drop back down. I'm not going to calculate this again, but you can take my word for it. There's no displacement in the y. And so we have, how long is this over for? 2 seconds. We're moving at 0 meters per second. And then between 5 and 9 over 4 seconds, we go from 0.4 to 0.6, which is 0.8. But the displacement, remember, is negative 0.8 divided by, in the meters, divided by 0.4 seconds is equal to 0.2 meters per second. And negative 0.2 meters per second. Can't forget that negative, because we have a negative displacement. Okay, so we end up going for 4 seconds. Oops, sorry. Went down a little too far. Negative 0.2 meters per second. And then the last part, we're standing still again for the last second. So it's going to jump back to 0. Doop, like that. Okay, so here, you now can pretty easily tell there's a direct relationship between the slope of the line of the position versus time graph and what's happening on the velocity versus time graph. This last example, and then you can also tell that if you have a negative or positive displacement, that changes the slope of the line and means you have a negative or positive velocity. Now, this is a little trickier. How do you calculate the change in velocity, or how do you create a velocity versus time graph for a position versus time graph that is constantly changing the rate? Well, I will show you. First thing that you want to do, over the first second, you can calculate the slope. So let's look at here. The slope is going to be, again, the rise, so how much we change in y, divided by the run, how much we change in x. So I'm just going to estimate this here. Let's say we end at 0.8 and we start at 0.4. So we've changed our rise here is about 0.4 meters over 1 second. So for our first second, we're going at about 0.4 meters per second. And I got that again by dividing 0.4 by 0.1. So that's where we start out. That's our initial velocity. So let's say here, we'll put a line, and again, this is a positive because remember, undo. We're going up here, not going down. Our rise is positive, so our velocity is going to be positive. So let's put a line, or we're going to put a point here at 0.4. And then it's a little hard to see. You know what, I'm actually going to erase the work that I just did here, but you all know how I got that. And just talk about what happens in the next second. So recall, we went up 0.4 and over 1. In the next second, note, now we're going over the same distance, so the run is still 1 second, but the rise has decreased almost by a half. So now we're going slower. And same thing, if you look at this next second, our run, undo. Our run is still going to be a second, but our rise is going up less and less and less. So this object is slowing down. So, and eventually, at this point, right here, for an instant, it stopped. So, if we start at 0.4 at time 0, then at 5 seconds, right here, the object is stopped. So that means I need to draw a straight line connecting these 2 points. 5 stopped, and then initially we're starting at 0.4 meters per second. So my velocity is going to be a straight line like this. It's not the straightest line, but you get the point. Okay, now let's look at what happens on the other side of 5 seconds. So now, notice this. Our run, again, is still 1 second. Here, 1. And our rise is now negative. We're going down. So it's a negative rise. So now, this is a negative slope. Here. And I'll just mark these here. You can see how the rises are getting bigger and bigger and bigger with their corresponding runs that are staying the same 1 second. But they're getting bigger and bigger and bigger in the negative direction. Remember, because we have a negative displacement all throughout, this point right here. We're changing, this whole line has a negative slope because it's going back towards 0. So, negative slope, and again, we'll say we end at exactly the same rate as we began. So if this was about 0.4 meters per second. Now we're going negative 0.4 meters per second, because that's the slope at this part of the line. So let's put a dot at negative 0.4, 10 seconds, and then connect. Oops. So overall, this looks like a straight line starting at 0.4 and ending at negative 0.4, with stopping right in the middle. And that's this motion. You start out fast, moving, start out quickly, moving away from the detector, and then you're slowing down until you stop, and then moving back towards the detector at an increasing rate. And that is it. Okay, so again, this is something that I think that you all kind of inferred over the course of working on these problems, but I just wanted to go through it with you. And I want to tell you something else. We haven't talked about this, but you can take the slope of the position versus time graph and use it to calculate a velocity versus time graph. And in the same manner, you can take a velocity versus time graph, its slope, and use it to calculate an acceleration versus time graph. So just really quickly here, this velocity versus time graph, what's the slope of this line? Well, the change in y is 0, and the change in x is 10. So the acceleration versus time graph here, this is 0 right here, is also going to be a straight line at 0. There's no change in the acceleration. We're not changing our speed. We're actually not moving at all. 0 acceleration. This, slightly more complicated. We have a velocity of 0.4 meters per second. But again, the slope of this line is 0. We're not changing our speed, constant velocity. Therefore, the acceleration versus time graph looks the same. It's when we get down here, this graph, where our acceleration versus time graph gets interesting. Okay, I am going to leave you with that, but I expect that given this velocity versus time graph, you could tell me what the acceleration versus time graph looks like, given that you know that you can use the slope of the velocity versus time graph to calculate the acceleration versus time graph. And that's what we're going to be working on tomorrow. Okay, this is a long screencast. Hope it's not too boring, and I'll see you all tomorrow.